This is Mary Peters with my Lab 7 Mass of a Black Hole Lab for Physics 2211, Section M02. Here's a description of the problem that was addressed in this lab. A star is orbiting a black hole of unknown mass. Assuming that the net force on the system is due solely to the gravitational force of the black hole, estimate the mass of the black hole. The information given included the mass of the star, position data points for the star, delta T between data points, and the position of the black hole. Here's a general method for how I solved the problem. I used the information given to program my computer to calculate the net force on the star throughout a loop. I set the net force equal to the force of gravity and solved for the mass of the black hole. I edited the code to print the mass of the black hole. Here's the VPython code that I used to solve this problem. First, I input the star's mass. I also inputted delta T, which was the time interval between the imported data points, which was approximately 1 day in seconds. And then I imported the position data, which is attached to this Excel file, which lists the x and y values after each delta. For the velocity calculation, I defined a starting index, and I set up my code to loop through different index values. So here's the loop. I calculated the velocity component-wise. So for the x component, I calculated delta x by properly defining the initial and final index values of adjacent data points. I then took the final minus the initial. To compute the x component of the velocity, I divided delta x by delta t, and the same procedure was followed for the y component. For my force calculation loop, I reset the starting index and had it once again loop through different index values. I used the velocity components to define the initial and final velocities. I then defined the initial and final momentum of the object by multiplying the initial and final velocity vectors by the mass of the star, because the definition of momentum is the product of mass times velocity multiplied by a proportionality factor gamma, which we assume to be 1 because the star is moving at a speed much less than the speed of light. This form of the momentum principle is known as the non-relativistic form. I then calculated delta V and delta P by doing the final velocity minus the initial velocity and the final momentum minus the initial momentum. I set dp dt equal to delta p over delta t by definition. I set Fnet equal to dp dt based on the derivative form of the momentum principle. Here is the derivative form of the momentum principle, and it can be found by dividing both sides of the momentum principle by delta t and then taking the limit as delta t approaches 0, and this states the instantaneous time rate. The rate of change of momentum can be separated into two components. One component gives the rate of change of the direction of the momentum, while the other gives the rate of change of the magnitude of the momentum. This is the rate of change of magnitude, and this component represents the rate of change of the direction. The rate of change of the direction of the momentum is equal to the perpendicular component of the net force. The rate of change of the magnitude of the momentum is equal to the parallel component of the net force. Here's the derivation. The momentum is factored into the product of the magnitude of the momentum and a unit vector in the direction of the momentum. The derivative is taken by applying the product rule. The definition of the parallel component of the momentum was used in the code. Then, Fnet perpendicular was found just by taking Fnet minus the parallel component. The mass of the black hole was calculated by setting the Fnet equal to the force of gravity between the black hole and the star, and this is the code that was used in order to print the mass of the black hole, and it was found that the mass was 3.18 times 10 to the 31 kilograms. The model does a good job of modeling the motion of the star. There are many arguments for the validity of this model. First, the star moves in an ellipse, so we can run it and see that it moves in an ellipse around the black hole. Second, Fnet is represented by the red arrow, and it is always pointing towards the black hole, which is good because the gravitational force is the only force acting on the object. And lastly, the value of the mass of the black hole is marked correct on the web sign. The black arrow represents Fnet parallel. It is always parallel or anti-parallel to the momentum of the star, causing the star to speed up or slow down. The blue arrow represents Fnet perpendicular. It causes the star to change directions. Here is the what does it mean question that was proposed. First, I will discuss how these quantities are related. The sum of the perpendicular and parallel components equals delta p over delta t. The directions of delta P over delta T and F net are the same. The values of these two vectors are equal to each other according to the momentum principle. The directions of the perpendicular components of the momentum and forces are the same, and values of the vectors are equal to each other. The directions of the parallel components of the momentum and force are the same, and the values of the vectors are equal to each other. Now I will discuss how they are different. F net and dP over dt are not the same. The momentum principle connects these two very different things. F net is found by summing the forces on the system, and change in momentum over change in time is found by analyzing the system's motion. If you know the net force, you know the momentum will change, and you can update the momentum. If, on the other hand, you observe the motion of an object and measure how its momentum is changing, you know what net force must be acting on the object. One way to summarize this relationship is to say that momentum change is caused by the net force. Here's the what-if question that was proposed. No, it is not possible for you to find a value for the mass of the new black hole that is different from the mass found for the original one because the net force on the object is calculated from the position data points for the system, and these do not change if the motion of the observed star remains